Salut tout le monde. Welcome back. Today is maybe a historic episode, you could say, for my channel. This is potentially the last differential geometry reading stream episode because my goal right now is to finish reading the last 4 sections of Differential Geometry by Erwin Kreisig. This is the finale on surfaces of constant Gaussian curvature. There's a lot that could be said at this point, being like it's the official end of the book. If you've been watching these videos throughout, I've been also reading the problems as well as the solutions. All of the solutions are conveniently in the back of the book. There are no problems in the remaining sections that I have to read except for the very last section, which is section 96. And so my goal is to not only read through to the end of section 96 today, but also to read the solutions to the 3 problems that are at the very end of the book, in keeping with the trend I started for myself with these episodes. So with that, let's just get right into it. Section 93. Pseudospherical surfaces of revolution. A surface of negative constant Gaussian curvature is called a pseudospherical surface. We will now investigate pseudospherical surfaces of revolution and shall obtain 3 different types. We set Gaussian curvature capital K equal to -1 over lowercase c squared, which is less than and not equal to 0. Then the differential equation 90.2. Technically, I read that in an earlier episode, which by the time you're watching this should already be uploaded, but at the time of my recording right now, I have not yet edited nor uploaded the episode where I read section 90. So just to refresh ourselves anyways, expression 90.2 is partial squared capital B partial U1 squared plus capital K times capital B equals 0, where capital B is equal to the square root of lowercase g sub 2, which is equal to the square root of lowercase g, where of course capital K denotes Gaussian curvature like I already mentioned, but lowercase g denotes the first fundamental form, so g sub 2 is a component of the first fundamental form. It's the coefficient of the second coordinate differential squared component term of the entire first fundamental form, so g sub 2 would be times du2 squared if you add coordinate directions u1 and u2 on your surface of interest. But lowercase g just by itself means the discriminant of the first fundamental form, which just in this case it's that all the other terms like g sub 1 g sub 1 2, or symmetrically g sub 2 1, they're not relevant to computing the square root of the discriminant of the first fundamental form. So that's 90.2. So that differential equation in this context of pseudospherical surfaces, we've got negative Gaussian curvature, has the solution square root of g sub 2 equals capital B, like I said, is equal to capital C sub 1 in terms of u2. That's not a square, that's a superscript, which denotes a contravariant tensor index, if you will. If it were a subscript, kind of like on that capital C, that's a covariant index. So we're going to move on. Capital C sub 1 in terms of u2 is then times the hyperbolic cosine of fraction u1 over a denominator of lowercase c, but then plus, outside of the hyperbolic cosine, we have capital C sub 2 in terms of u2, then times hyperbolic sine of u1 over lowercase c. So first, we introduce geodesic parallel coordinates u1, and that should read u2, but that is a mistranscription in the PDF. So u1 and u2, so that the coordinate curve u1 equal to 0 is a curve of constant geodesic curvature, 1 over lowercase c. The coordinate curves u2 equal to a constant are geodesics orthogonal to the curve where u1 equals 0, and the coordinate curves where u1 are equal to a constant are geodesic parallels of a curve where u1 equals 0. Now, since the coefficient of the first fundamental form that I talked about, g sub 1 equals 1, then we have from expression 49.9a which is a statement for principal curvature with geodesics here. We have quantity kappa sub g closed quantity, then with a subscript of u with a superscript 1 equal to a constant. So we're dealing with contravariant indices, that's all good, equals 1 over a denominator of 2 times g sub 2 2, then times the square root of g sub 1 1. And then that fraction is then times partial g sub 2 2 partial u1, which then is equal to 1 over the square root of g sub 1 1, then times partial with respect to u1 of the logarithm of the square root of g sub 2 2. So we have from that, returning back to section 93 now, we have quantity kappa sub g closed quantity, then with a subscript of u1 equal to 0 equals 1 over the square root of g sub 2 2, then times partial square root g sub 2 2 partial u1 equals 1 over lowercase c, where lowercase c is greater than non-equal to 0. So from expression 93.1, which is a solution for a second order linear differential equation, which is derived from a relation for Gaussian curvature in terms of coefficients of the first fundamental form. From that solution, which is above, we obtain square root of g sub 2 2, where u1 is equal to 0, and we have u2 just kind of free. That is equal to, let's call it capital C sub 1 in terms of just u2. And then we also have that partial of square root of g sub 2 2 partial u1 evaluated, where u1 is equal to 0. We're going to call this capital C sub 2 in terms of u2 all over lowercase c. So consequently, capital C sub 1 is equal to capital C sub 2. And if we choose u2 proportional to the arc length sigma of the curve where u1 is equal to 0, that is where u2 is equal to sigma over lambda, then since the hyperbolic cosine of u1 over c plus the hyperbolic sine of u1 over c is equal to e to the u1 over lowercase c, then we have that ds squared is equal to du1 squared plus lambda squared, then times e to the 2 times u1 over c, and then times du2 squared, so that's the first fundamental form, where lambda, which is non-zero, is a constant. And then from the previous section 92, there was a relation for the first fundamental form when we have a spherical surface of revolution, and so that's what 92.2 is. And what we just read in the line above, 93.2, those two expressions become identical if u1 over bar is equal to lambda times e to the u1 over lowercase c, and u2 over bar is equal to u2. Then we're able to set x3 equal to the integral of the square root of the quantity 1 minus lambda squared over lowercase c squared, then times e to the 2 times u1 over lowercase c closed quantity du1. And inserting these expressions into, again, an expression from the previous section 92, which is the vector parametric representation of a spherical surface of revolution. It's x in terms of u1 over bar and u2 over bar, which is equal to 3 entries entry-wise, u1 over bar times cosine of u2 over bar. Then the next entry is u1 over bar times the sine of u2 over bar. And then the third and final entry is the function h, which is in terms of u1 over bar. So inserting these expressions into that vector parametric form of a spherical surface of revolution, then we obtain a representation of pseudo-spherical surfaces of revolution, which are called parabolic pseudo-spherical surfaces of revolution, or pseudospheres. And we have an image of this in figure 98b, which I'll just kind of superimpose that on the screen right now. So from the above relation for u1 over bar and u2 over bar, we have u1 is equal to lowercase c times the logarithm of u1 over bar over lambda, and correspondingly du1 is equal to lowercase c over u1 over bar, then times du1 over bar. And therefore, x3 is equal to the integral of lowercase c over u1 over bar, then times the square root of the quantity 1 minus the fraction u1 over bar squared over a denominator of lowercase c squared closed quantity du1 over bar. Again, we have poor transcription of the PDF, but what it intends to say here is if we set u1 over bar equal to lowercase c times cosine of alpha, then du1 over bar not tilde, is equal to negative c times the sine of alpha d alpha, and by a suitable choice of the sign of the square root, then we have that x3 is equal to lowercase c times the integral of sine squared of alpha over the cosine of alpha d alpha, which then resolves to be equal to lowercase c times the quantity, which is the logarithm of the tangent of the quantity alpha over 2 plus pi over 4, and then close the argument of the logarithm of the tangent, and then that's minus sine alpha, and then we close the entire quantity. Together with u1 over bar equal to lowercase c times cosine of alpha, this is a parametric representation of the meridian of the pseudosphere. We may write this more elegantly as u1 over bar equals lowercase c times the hyperbolic secant of lowercase t, and x3 is equal to lowercase c times the quantity t minus hyperbolic tangent of t closed quantity, where lowercase t is equal to the logarithm of the quantity secant alpha minus tangent alpha closed quantity. This curve is known as a tractrix. The tractrix, first considered by none other than, I believe it's George Wilhelm Friedrich Leibniz, is Sir Leibniz's full name. So the tractrix, first considered by Leibniz in 1693, is the path of a moving heavy particle capital P, which is connected with a point capital Q by a thread of constant length lowercase c. The point Q is moving along a straight line which does not contain the point P, for which we can refer to figure 96 here below. Indeed, we can easily see that the segment of the tangent to the tractrix between the x3 axis and the point capital P always has the constant length lowercase c. Since dx3 du1 over bar equals tangent of alpha, we see that alpha is the angle between the tangent to the meridians of the pseudosphere and the x1, x2 plane. For every plane curve y of x, the length lowercase c of the segment of the tangent between the point of contact and the x-axis is given by the formula lowercase c equals y over y prime, then times the square root of the quantity 1 plus y prime squared closed quantity, where the prime denotes the derivative with respect to x, and we can refer to figure 97, which I scrolled past just now above. Hence, y prime is equal to a fraction with the numerator of y and a denominator of the square root of the quantity lowercase c squared minus y squared closed quantity, or x is equal to plus or minus the integral of lowercase c over y, then times the square root of the quantity 1 minus y squared over c squared closed quantity dy. And this corresponds to the expression for x3, which I read previously as expression 93.5 above. Part 2, we choose geodesic parallel coordinates u1 and u2 so that the curve u1 equal to 0 is a geodesic, or as people in the United Kingdom would say, a geodesic, and the curves u2 equal to a constant are geodesics orthogonal to the curve where u1 is equal to 0. Then, since quantity kappa sub g closed quantity and then a subscript of u1 equals 0 is equal to 0, we have that partial capital B partial u1 evaluated where u1 is equal to 0 is equal to 0, in the same manner as in the preceding section. Hence, in our expression for the square root of g sub 2, we have that capital C sub 2 is equal to 0. Consequently, by a suitable choice of the coordinate u2, the first fundamental form becomes ds squared equals du1 squared plus lambda squared times the square of the hyperbolic cosine of u1 over c, then times du2 squared, where non-zero lambda denotes a constant. And this expression, which I just read, as well as an expression from the previous section, 92, for the first fundamental form of a spherical surface of revolution with constant Gaussian curvature. These expressions are identical if quantity 1 plus h prime squared closed quantity then times du1 over bar squared equals du1 squared, and u1 over bar equals lambda times hyperbolic cosine of u1 over lowercase c, and finally u2 over bar equals u2. Then we have that x3 is equal to the integral of the square root of the quantity 1 minus lambda squared over lowercase c squared times hyperbolic sine squared of u1 over c closed quantity du1. And inserting these expressions into the vector parametric representation of a spherical surface of revolution with constant Gaussian curvature, I believe that's what expression 92.1 is, we obtain a representation of a surface which is called a hyperbolic pseudospherical surface of revolution, for which we can refer to a depiction in figure 98a. which I'll just superimpose on the screen right now. The function x3 is an elliptic integral, for which refer to the preceding section, whose values are real if the square of the hyperbolic sine of u1 over lowercase c is less than or equal to c squared over lambda squared. Consequently, the values of the radius, again transcription error, but that should be u1 over bar, are restricted to the interval where u1 over bar is greater than or equal to lambda, or u1 over bar is also less than or equal to the square root of the quantity lambda squared plus c squared closed quantity. Since x3 is periodic, the surface consists of a succession of congruent zones. These zones are spool-like. The circles by which every zone is bounded have the radius u1 over bar equals the square root of the quantity lambda squared plus c squared closed quantity, where the radius of the circle in the middle of every zone is u1 over bar equals lambda. From the previously read requirements for what we're dealing with to be equal to the representation given in the preceding section, we obtain that dx3 du1 over bar is equal to the square root of the quantity, which is a fraction, with the numerator of c squared plus lambda squared minus u1 over bar squared, all over a denominator of u1 over bar squared minus lambda squared closed quantity. Thus, at the points of the boundary of the zones, the tangent plane of the surface is parallel to the x1, x2 plane, while in the middle of every zone, it is parallel to the axis of revolution. The maximum parallels are cuspidal edges of the surface. And now we are at part 3 of this section. We finally choose geodesic polar coordinates u1 star and u2 star. Then from g sub 2 star, where u1 star is equal to 0 and we leave u2 star free, being equal then to 0, and also having partial of square root of g sub 2 star, partial u1 star evaluated at u1 star equal to 0, then being equal to 1 in our, let's say, governing relation for the square root of g sub 2 that we've been dealing with in this section, we obtain that capital C sub 1 is equal to 0 and capital C sub 2 is equal to lowercase c. Consequently, ds squared is equal to du 1 star squared plus lowercase c squared times the square of hyperbolic sine of u1 star over lowercase c, then times du2 star squared. If we set u1 equal to u1 star and u2 equal to lowercase c over lambda then times u2 star, we have that ds squared equals du1 squared plus lambda squared times the square of hyperbolic sine of u1 over c then times du2 squared. And this becomes identical with a similar statement from the preceding section if u1 over bar equals lambda times hyperbolic sine of u1 over c, and if u2 over bar equals u2, and if quantity 1 plus h prime squared closed quantity then times du1 over bar squared equals du1 squared, then we have that x3 equals the integral of the square root of the quantity 1 minus lambda squared over c squared, then times the square of hyperbolic cosine of u1 over lowercase c closed quantity du1. If we insert these expressions into the vector parametric representation for a spherical surface of revolution with constant Gaussian curvature, actually it's not spherical, it's pseudo-spherical if I'm mistaken or not mistaken, depending on how you look at it. We obtain a representation of a surface which is known as an elliptic pseudo-spherical surface of revolution, which is depicted in figure 98c. x3 is again an elliptic integral. Hence, the surface consists of congruent zones. For real values of the argument, the hyperbolic cosine is greater than or equal to 1. Consequently, in order that x3 be real, we have to require that lambda squared is less than or equal to lowercase c squared. Hence, the radius varies in the interval u1 over bar greater than or equal to 0 and u1 over bar less than or equal to the square root of the quantity lowercase c squared minus lambda squared closed quantity. The direction of the tangent to the meridians can be obtained from the expression 93.10. Thus, dx3 du1 over bar is equal to the square root of the quantity, which is the fraction with a numerator of lowercase c squared minus lambda squared minus u1 over bar squared, all over a denominator of u1 over bar squared plus lambda squared closed quantity. At the boundaries of the zones, the tangent is parallel to the x1, x2 plane, for which refer to the picture in figure 98c above. We now come to section 94 on geodesic mapping. This one's relatively short here. In order to consider the geodesic mapping of surfaces of constant Gaussian curvature, we first state some general facts on geodesic mappings. An allowable mapping, whose definition was given in section 56, which is the first section of chapter 6, which was on mappings. You can go back and watch that episode if you want. An allowable mapping of a portion capital S of a surface onto a portion S star of a surface is said to be geodesic if to each geodesic arc on either portion there corresponds a geodesic arc on the other. Theorem 94.1. An allowable mapping of a portion S of a surface onto a portion S star of a surface is geodesic if and only if the Christoffel symbols, Christoffel sub alpha beta superscript gamma on S and Christoffel star sub alpha beta superscript gamma on S star with respect to the same Gaussian coordinates on S and S star are connected by the relations Christoffel sub alpha beta superscript gamma equals Christoffel star sub alpha beta superscript gamma plus Kronecker delta sub alpha superscript gamma then times partial lowercase h partial u superscript beta star plus Kronecker delta sub beta superscript gamma then times partial lowercase h partial u superscript alpha star, where lowercase h is equivalent to 1/6 times the logarithm of lowercase g over lowercase g star, where lowercase g star and lowercase g are the discriminants of the first fundamental forms of surface portion S star and S, respectively. And just as a note, if this is the first one you've watched in a while, I realize that a Christoffel symbol is denoted by a capital gamma. I just read it out loud as Christoffel because, with all these integrals that are floating around, who knows if maybe, like a gamma function or a Bessel function, which is defined in terms of a gamma function, pops up somewhere in your calculations, your proof, whatever it is that you're working on. I just say Christoffel, but also it's maybe worth noting that Elwin Bruno Christoffel himself, in the original primary source publication where he introduced what we now refer to as a Christoffel symbol, he didn't even denote it with the capital gamma. And if you want to read what might be the only English translation on the web of that original German publication by Elwin Bruno Christoffel, go to my website, anthonymakesvideos.com/files, and you can read that there. But that's just my convention for how I've been reading this book out loud here on the internet. So the proof of theorem 94.1 is as follows. We start from the differential equations in section 51 of the geodesics on the portion of the surface S. So 51.4, just to remind ourselves, we have lowercase s double prime over lowercase s prime then times u superscript tau prime minus Christoffel sub nu sigma superscript tau then times u superscript nu prime then times u superscript sigma prime then minus u superscript tau double prime is equal to 0. Back to section 94, we have u superscript tau prime then times lowercase s double prime then minus the quantity Christoffel sub nu sigma superscript tau then times u superscript nu prime then times u superscript sigma prime plus u superscript tau double prime closed quantity then times lowercase s prime is equal to 0, where tau is equal to 1 or 2. So we start from those differential equations and we eliminate lowercase s prime and lowercase s double prime. So we now have u1 prime then times quantity u2 double prime plus Christoffel sub nu sigma superscript 2 then times u superscript nu prime then times u superscript sigma prime closed quantity minus u2 prime times quantity u1 double prime plus Christoffel sub nu sigma superscript 1 then times u superscript nu prime then times u superscript sigma prime closed quantity. This equals 0. Similarly, the differential equation of the geodesics on the portion of a surface S star is u1 star prime then times quantity u2 star double prime plus Christoffel star sub nu sigma superscript 2 then times u v star prime times u sigma star prime closed quantity minus u2 star prime times quantity u1 star double prime plus Christoffel star sub nu sigma superscript 1 then times uv star prime times u sigma star prime closed quantity equals 0, where u1 star and u2 star are the coordinates on the portion of a surface S star. The coordinates on S and S star are assumed to be the same. That is, the mapping under consideration is defined by u1 star equals u1 and u2 star equals u2. If we subtract expression 94.3 above from expression 94.2 above, we obtain bracketed outer quantity u1 prime times the quantity Christoffel sub nu sigma superscript 2 minus Christoffel star sub nu sigma superscript 2 closed quantity minus u2 prime times a quantity Christoffel sub nu sigma superscript 1 minus Christoffel star sub nu sigma sigma superscript 1 close quantity and close outer square bracket quantity, then times uv prime times u sigma prime equals 0. In consequence of the transformation law of the Christoffel symbols of the second kind, which is given in section 47, to remind ourselves, we have Christoffel sub alpha beta superscript gamma times partial u over bar sigma partial u gamma equals Christoffel over bar sub lambda epsilon superscript sigma times partial u over bar lambda partial u alpha times partial u over bar epsilon partial u beta plus partial square u over bar sigma partial u alpha partial u beta. In consequence of that transformation law for Christoffel symbols, we have Christoffel sub nu sigma superscript alpha minus Christoffel star sub nu sigma superscript alpha equals quantity Christoffel over bar sub, that's an eta epsilon superscript kappa minus Christoffel over bar star sub eta times epsilon superscript kappa close quantity partial u over bar eta partial u nu then times partial u over bar epsilon partial u sigma then times partial u alpha partial u over bar kappa. Hence, the expressions d sub nu sigma superscript alpha equals Christoffel sub nu sigma superscript alpha minus Christoffel star sub nu sigma superscript alpha are the components of a tensor of third order, contravariant of first order, and covariant of second order. The equation 94.4 above, which involved that bracket outer quantity times uv prime u sigma prime equals 0, must be satisfied identically. Otherwise, only 3, but not like one-dimensional infinity, g at S6 would pass through every point of S and S star. In consequence of the expression for d sub nu sigma superscript alpha, we may write expression 94.4 in the form quantity u1 prime then times d sub nu sigma superscript 2 minus u2 prime then times d sub mu sigma superscript 1 close quantity then times uv prime then times u sigma prime is equal to 0. This is identically satisfied if d sub 1 superscript 1 is equal to 2 times d sub 1 superscript 2. Furthermore, if d sub 1 superscript 2 is equal to d sub 2 superscript 1 is equal to 0, and d sub 2 superscript 2 is equal to 2 times d sub 1 superscript 1. These conditions can also be written in the form 3 times d sub nu sigma superscript alpha minus Kronecker delta sub nu superscript alpha then times d sub sigma beta superscript beta minus Kronecker delta subscript sigma superscript alpha then times d sub nu beta superscript beta is equal to 0, or in consequence of expression 94.5 above, we also have Christoffel sub nu sigma superscript alpha is equal to Christoffel star sub nu sigma superscript alpha plus 1/3 times the quantity delta sub nu superscript alpha then times d sub sigma beta superscript beta plus delta sub sigma superscript alpha then times d sub nu beta superscript beta closed quantity, as can be easily verified. And if we insert that into expression 94.2, then we obtain expression 94.3. That is, the expression that I had most recently read, 94.6, is the necessary and sufficient condition for the mapping under consideration to be geodesic. Since d sub sigma beta superscript beta equals Christoffel sub sigma beta superscript beta minus Christoffel star sub sigma beta superscript beta, which equals partial with respect to u sigma of the quantity logarithm of the square root of g minus the logarithm of the square root of g star closed quantity, which is all equal to then 1/2 times partial with respect to u sigma of the logarithm of g over g star, and d sub nu beta superscript beta is equal to 1/2 times partial with respect to u nu of logarithm of g over g star, for which we can refer back to 47.6 prime, which is just an identity for a Christoffel symbol where we have Christoffel sub alpha gamma superscript alpha is equal to 1/2g times partial u gamma, which is equal to partial u gamma of the logarithm of the square root of g. So we see that expressions 94.1 and 94.6 are identical. And thus, from theorems 57.1 and 94.1, we obtain theorem 94.2, which states that any isometric mapping is geodesic. This also follows immediately from theorem 57.2. To save time from reading theorems 57.1 and 57.2 in their entirety, I'm just going to put them on the screen. Those have come up multiple times in this last little end of the book. So, moving on. Section 95. Geodesic mapping of surfaces of constant Gaussian curvature. Eugenio Beltrami discovered the following interesting theorem 95.1. If a portion capital S of a surface can be mapped geodesically onto a portion capital S star of a surface of constant Gaussian curvature capital K star, the Gaussian curvature capital K of the portion of a surface capital S must also be constant. And the proof is as follows, which is the entirety of this section. We use from the previous section, which I just read, theorem 94.1 and the corresponding notations. We assume that the portion capital S of the surface is geodesically mapped onto the portion capital S star. Then, in consequence of expression 94.1, we find a relation between the curvature tensor, which was given all the way back in section 46. It's the full big bad mixed Riemann curvature tensor. Capital R superscript sigma sub alpha lambda beta equals partial Christoffel sub alpha beta superscript sigma partial U lambda minus partial Christoffel sub alpha lambda superscript sigma partial U beta plus Christoffel sub alpha beta superscript kappa, then times Christoffel sub kappa lambda superscript sigma minus Christoffel sub alpha lambda superscript kappa, then times Christoffel sub kappa beta superscript sigma. And if you want to see some calculations involving the full Riemann curvature tensor, head on over to anthonymakesvideos.com/files and you can see the work of a reader filling in the gaps of Bernard Riemann's habilitation thesis, which inaugurated Riemannian geometry and played around with the so-called Riemann curvature tensor in that document, which you can find on my website. But going back to section 95, we're going to formulate our curvature tensor now specifically as, with the following indices, that is, capital R superscript sigma sub mu eta nu equals partial with respect to U eta of Christoffel sub mu nu superscript sigma minus partial with respect to U nu of Christoffel sub mu eta superscript sigma plus Christoffel sub mu nu superscript kappa, then times Christoffel sub kappa eta superscript sigma minus Christoffel sub mu eta superscript kappa, then times Christoffel sub kappa nu superscript sigma, and the curvature tensor capital R star superscript sigma sub mu eta nu of the portion of surface capital S star. By inserting expression 94.1 into all of this, then we obtain capital R superscript sigma sub mu eta nu equals capital R star superscript sigma sub mu eta nu plus Kronecker delta sub nu superscript sigma, then times the quantity partial squared h partial u mu partial u eta minus partial h partial u kappa times Christoffel star sub mu eta superscript kappa minus partial h partial u mu, then times partial h partial u eta closed quantity minus Kronecker delta sub eta superscript sigma, then times quantity partial squared h partial u mu partial u nu minus partial h partial u kappa, then times Christoffel star sub mu nu superscript kappa minus partial h partial u mu, then times partial h partial u nu closed quantity. This is equivalent to capital R superscript sigma sub mu eta nu equals capital R star superscript sigma sub mu eta nu plus Kronecker delta sub nu superscript sigma, then times the quantity lowercase h subscript comma mu eta minus lowercase h subscript comma mu, then times lowercase h subscript comma eta closed quantity minus Kronecker delta sub eta superscript sigma, then times quantity lowercase h subscript comma mu nu minus h subscript comma mu, then times h subscript comma nu closed quantity, where the indices preceded by a comma indicate covariant derivatives with respect to the metric tensor g star sub alpha beta of capital S star. So that's a little bit tricky notation, but if you've been following along with the previous episodes, then we did see that before in previous chapters. So for the sake of simplicity, the first partial derivatives of h are also written in the symbolism of absolute differentiation. This is justified by the fact that in the case of a scalar, the covariant derivative and the usual partial one are the same. This is a huge hand wave, in my opinion. By contraction with respect to sigma and nu, we have capital R sub mu eta equals capital R star sub mu eta plus h subscript comma mu eta minus h subscript comma mu times h subscript comma eta. The quantity is capital R subscript mu eta, which equals capital R superscript sigma sub mu eta sigma, and capital R star sub mu eta, which is equal to capital R star superscript sigma sub mu eta sigma, are the components of the so-called Ricci tensor of S and S star respectively. That's also called in some places, if I'm not mistaken, like scalar curvature, like a scalar curvature tensor, because the full Riemann curvature tensor, the mixed Riemann curvature tensor where we've got covariant and contravariant indices in the mix, once you do that contraction, where I said that's a huge hand waving step with respect to sigma and nu, then we get, so we have Riemann full curvature tensor, take a contraction, now we have scalar Ricci curvature. I did that by hand in my work of reader exercise, filling in the gaps of Bernard Riemann, habilitation, geometry, hibbity hoobla, skibbity toilet. AnthonyMakesVideos.com/merch. Get yourself a figure 69 cone t-shirt. You can see on my AnthonyMakesVideos.com/files, and then find, it's like diffgeo32.pdf or whatever it is. I actually by hand work out the details of a tensor contraction going from the mixed Riemann curvature tensor definition and then going to the scalar Ricci curvature tensor. It looks slightly different from what's right here because what I have in my document on the website, I was trying to fit it into a form where I could do like the Louisville isothermic coordinate differential equation like form that it would all fit together so I could spit it all out in the end and you would get that stereographic projection formula looking thing that was in Bernard Riemann's habilitation thesis. So it's kind of like all the way back at the beginning of the year, that was like 6, 8, 9 months ago now that I did that, or however long ago. And now it's like we're squaring the circle, and you know, not only are we inscribing a circle in a given square, but we're putting a square around the given circle. How about that, Euclid? Okay, anyways, moving on. These quantities are closely related to the Gaussian curvature, which was defined all the way back in section 46. I'm not going to reread that because, you know, we just, here in differential geometry, gang, we know what all of the things on the formula sheet are without having to look at the formula sheet. Okay, that's what it means to go back to before Socrates and Plato, a la Heidegger. We're going to say no thanks Descartes, no thanks Newton. We're going to say no thanks Erwin Kreisig, say no to coordinates. We're going to go back to Neo-Pythagoreanism. You know what I'm saying? You probably don't. Memorize the formula sheet, that's all I'm saying. And lift weights and practice your takedowns. Anyways, Gaussian curvature, capital K star is equal to lowercase b star over lowercase g star, which is equal to capital R star sub 1212 over lowercase g star. In fact, that's literally the whole capital K equals R sub 1212 over G. That's what I started off with in my filling in the gaps of Bernard Riemann's habilitation thesis. I literally went from that to the whole like ds square equals whatever, ds over square root of 1 plus 4 times capital K. So it was something like that. You know what I'm saying? I went all the way from that. I'm going to stop ranting. So we obtain immediately capital R star superscript sigma sub mu eta nu equals lowercase g star superscript sigma alpha, then times capital R star sub alpha mu eta nu equals capital K star, then times a quantity Kronecker delta sub eta superscript sigma, then times g star sub mu nu minus Kronecker delta sub mu superscript sigma, then times g star sub mu eta closed quantity. By contraction with respect to sigma and nu, we find that capital R star sub mu eta equals negative capital K star times G star sub mu eta, since Kronecker delta sub nu superscript nu is equal to 2. Analogously, when we have capital R sub mu eta equal to negative capital K times lowercase g sub mu eta, where g sub mu eta are the components of the metric tensor of. Hence, expression 95.3, which I read above here, that's the scalar Ricci curvature tensor, becomes h subscript comma mu eta equals h subscript comma mu then times h subscript comma eta plus capital K star times lowercase g star sub mu eta minus capital K then times lowercase g sub mu eta. Using the assumption that capital K star is constant, we will prove that the first partial derivatives of K with respect to u1 and u2 vanish. That is, that K must be constant. In order to obtain those derivatives, it is natural to take the covariant derivative of the expression 95.5 with respect to g star sub alpha beta. Since g star sub mu eta comma kappa equals 0, for which we can refer to theorem 72.1. To remind ourselves, that is a theorem due to Ricci himself, Gregorio Ricci Cubastro, that is. The covariant derivatives of the tensors g sub alpha beta, g superscript alpha beta, and Kronecker delta sub alpha superscript beta are zero tensors. So from that, we obtain in this manner that h subscript comma mu eta kappa is equal to h subscript comma mu kappa then times h subscript comma eta plus h subscript comma mu times h subscript comma eta kappa minus capital K sub comma kappa then times lowercase g sub mu eta minus capital K times lowercase g sub mu eta comma kappa. We now determine the covariant derivative g sub mu eta comma kappa from 47.4, which is where the first partial derivatives of the coefficients g sub alpha beta of the first fundamental form can be represented as a sum of two Christoffel symbols of the first kind, namely partial g sub alpha beta partial u kappa is equal to Christoffel sub alpha kappa beta plus Christoffel sub beta kappa alpha, which is equal to g sub lambda beta times Christoffel sub alpha kappa superscript lambda plus g sub lambda alpha times Christoffel sub beta kappa superscript lambda. From this, we have that partial g sub mu eta partial u kappa is equal to g sub sigma eta times Christoffel sub mu kappa superscript sigma plus g sub mu sigma times Christoffel sub eta kappa superscript sigma. Hence, from the beginning of section 94, by the relation for the connection given a geodesic mapping from the preceding section, we have partial g sub mu eta partial u kappa is equal to g sub sigma eta times the quantity Christoffel star sub mu kappa superscript sigma plus Kronecker delta sub mu superscript sigma times lowercase h subscript comma kappa plus Kronecker delta sub kappa superscript sigma times h sub comma mu closed quantity plus g sub mu sigma times quantity Christoffel star sub eta kappa superscript sigma plus Kronecker delta sub eta superscript sigma times h subscript comma kappa plus Kronecker delta subscript kappa superscript sigma times h subscript comma eta closed quantity. Hence, by expression 71.3 double prime, which is from section 71 on absolute differentiation of tensors of arbitrary order, we have a sub alpha beta comma sigma is equal to partial a sub alpha beta partial u sigma minus a sub gamma beta times Christoffel sub alpha sigma superscript gamma minus a sub alpha gamma times Christoffel sub beta sigma superscript gamma. By this, we have that g sub mu eta comma kappa is equal to partial g sub mu eta partial u kappa minus g sub sigma eta times Christoffel star sub mu kappa superscript sigma minus g sub mu sigma times Christoffel star sub eta kappa superscript sigma equals 2 times g sub mu eta times h sub comma kappa plus g sub kappa eta times h sub comma mu plus g sub mu kappa times h sub comma eta. Boy, reading this out loud is one of the trickiest tongue twisters of the entire book, if I do say so myself. Okay, inserting this expression into the aforementioned expression 95.6 and replacing the expressions capital K times lowercase g sub mu eta, etc., then by means of expression 95.5 above, we obtain h subscript comma mu eta kappa equals 2 times the quantity h sub comma mu times h sub comma eta kappa plus h sub comma eta times h sub comma kappa mu plus h sub comma kappa times h sub comma mu eta closed quantity minus, and then this is kind of like a pedagogical criticism of the typesetting of the equations by Erwin Kreisig. As we all know from elementary school algebra, negative times a negative is a positive, subtracting a negative same as adding magnitude of whatever that negative scalar was. So the continuation of the line, it almost looks like there's two minuses. So why not just plus? Well, there should just be one minus. It's all on one line. Anyways, so we have 2 times that quantity. Then we have minus 4 times h sub comma mu times h sub comma eta times h sub comma kappa minus capital K star times the quantity 2 times lowercase g star sub mu eta, then times h subscript comma kappa plus g star sub eta kappa times h subscript comma mu plus g star sub kappa mu times h subscript comma eta closed quantity minus capital K sub comma kappa times lowercase g sub mu eta. From this, it follows that h subscript comma mu eta kappa minus h subscript comma mu kappa eta equals capital K star times the quantity lowercase g star sub mu kappa times h subscript comma eta minus g star sub mu eta times h subscript comma kappa closed quantity minus capital K subscript comma kappa times lowercase g sub mu eta plus capital K subscript comma eta then times lowercase g sub mu kappa. On the other hand, from expression 73.5, which to remind ourselves states a sub beta comma sigma mu minus a subscript beta comma mu sigma is equal to a sub eta times Riemann curvature tensor capital R superscript eta lower subscript beta sigma mu. And expression 95.4 above, we have h subscript comma mu eta kappa minus h subscript comma mu kappa eta equals h subscript comma sigma times Riemann curvature tensor capital R star superscript sigma subscript mu eta kappa equals h subscript comma sigma then times capital K star then times quantity Kronecker delta sub eta superscript sigma then times g star sub mu kappa minus Kronecker delta sub kappa superscript sigma times g star sub mu eta closed quantity equals capital K star times the quantity lowercase g star sub mu kappa times h subscript comma eta minus g star sub mu eta times h subscript comma kappa closed quantity. In consequence of expression 95.7 above, we obtain from this that g sub mu kappa times capital K sub comma eta minus g sub mu eta times capital K sub comma kappa equals 0. Since the determinant lowercase g of the coefficients of this system of linear equations is different from 0, the only solutions are the trivial ones, namely where capital K subscript comma alpha is equal to 0, where alpha can be equal to 1 or 2. Hence, capital K is a constant, and this completes the proof. All right, you guys, this is historic. We are at the last section of the book. We're about to finish reading Differential Geometry by Erwin Kreisig out loud on the internet. Section 96, Surfaces of Constant Gaussian Curvature and Non-Euclidean Geometry. All right, let's get it. We conclude our study of surfaces of constant Gaussian curvature, capital K non-zero, by proving the fact that the intrinsic geometry of these surfaces, or at least locally, is identical with non-Euclidean geometry. We first make some remarks on non-Euclidean geometry. Further details can be seen in the appropriate literature. For instance, the work titled Non-Euclidean Geometry, published in 1957 by H.S.M. Coxeter in his famous 13 books, Euclid, circa 325 BC, that is to say, Euclid was after Plato. He was before Apollonius of Perga. And is it Pegra or Perga? I forgot. I've mentioned this before. I believe it was in my episode 5 or 6 where I did the first philosophical rant of the differential geometry reading stream series. I talked about how geometry was as good as it gets with Apollonius of Perga before Descartes would come along, 1,000 years later or so. Or maybe it was more than that, because Apollonius of Perga, I forgot if he was 400 Apollonius of Perga had to be 80, I believe, 480, something like that. Either way, Descartes was at least 1,000 years after Apollonius of Perga, feels like. In his famous 13 books, Euclid investigates the foundations of geometry. He starts with 23 definitions, which are followed by 5 postulates and 5 axioms. The 5th axiom is as follows. If a straight line meet 2 other straight lines so as to make the 2 interior angles on one side of it together less than 2 right angles, the other straight lines will meet if produced on that side on which the angles are less than 2 right angles. This axiom is equivalent to the statement that there is only one straight line, capital G sub 1, parallel to a given line, capital G, and passing through a point, capital P, not on G. The other axioms are much more self-evident than this one. Hence, it was conjectured even a long time ago that the fifth axiom was not even an axiom, but a theorem, that is, a consequence of the others. Many attempts have been made by a great number of outstanding mathematicians to deduce this, quote, theorem, unquote, from the other axioms. Since no attempt turned out to be successful, Gauss drew the conclusion that the fifth axiom could not be proved at all. In 1792, he started working on the foundations of a geometry in which this axiom is replaced by a contrary assumption, and by 1816 at the latest, he had gained a clear idea of such a geometry. He did not publish anything on this matter. Nikolai Lobachevsky, who lived from 1793 to 1856, was the first to state publicly, in 1829 that is, the existence of a geometry which is independent of the fifth axiom of Euclid. Independently, Bolyai, who lived from 1802 to 1860, published similar results in 1832. Both investigations were concerned with the so-called hyperbolic non-Euclidean geometry. This geometry is, at least locally, identical with the intrinsic geometry of the surfaces of negative constant Gaussian curvature, as was shown by the investigations of Eugenio Beltrami. The importance of this paper consists especially in the fact that it makes evident that the hyperbolic non-Euclidean geometry can never lead to contradictions, since contradictions of this kind would also cause contradictions in the intrinsic geometry of the above surfaces. Since those surfaces are embedded in three-dimensional Euclidean space, R3, the aforementioned contradictions would lead to contradictions in Euclidean geometry. Hyperbolic non-Euclidean geometry can briefly be characterized by the fact that there are at least two straight lines passing through a point and parallel to a given line, and the sum of the angles of a triangle is less than pi. And I will note, I don't have time to work it out right now, but you can verify this using the Gauss-Bonnet theorem, showing that if you have a triangle on a sphere, the sum of the interior angles is greater than pi. If you're on a surface of negative Gaussian curvature, like say, around a saddle point, saddle surface, looks like a Pringle, you have a triangle on there, then the sum of the interior angles of that triangle is going to be less than pi. So if you want to show that, you can use the Gauss-Bonnet theorem. Don't have time to do that right now. Another type, the so-called elliptic non-Euclidean geometry, was first investigated by Bernard Riemann in Über die Hypothesen welcher der Geometrie zugrunde liegen, his habilitation thesis, which inaugurated the eponymous Riemannian geometry. In this geometry, there does not, and then when I say Riemannian geometry, that's not what I'm referring to as the geometry here, but in this geometry, there does not exist a straight line parallel to a given one. I'm talking about negative constant Gaussian curvature, hyperbolic geometry, if you will, not spherical, that is. So in this geometry, the sum of the angles of a triangle is greater than pi. So to recap, spherical, triangle on the surface, interior angles greater than pi. Hyperbolic, negative constant Gaussian curvature, sum of the interior angles of triangle less than pi. Moving on. The intrinsic geometry of any surface of positive constant Gaussian curvature is, at least locally, identical with elliptic non-Euclidean geometry. Clear insight into the intrinsic geometry of a pseudo-spherical surface, capital S, can be obtained by a certain conformal mapping, which is due to none other than Henri Poincaré, who lived from 1854 to 1912. So a certain conformal mapping of this pseudo-spherical surface, capital S, into a plane under which mapping the geodesics on, capital S, correspond to certain semicircles in the plane. In order to introduce this mapping, we first prove the following. Theorem 96.1. If a surface capital S can be mapped conformally into a plane capital E so that the geodesics of capital S correspond to circles in capital E, the Gaussian curvature capital K of the surface capital S must be constant, and the proof is as follows. We assume that the same coordinates have been introduced on capital S and the plane capital E. Then, since the mapping of S into E is assumed to be conformal at corresponding points, the coefficients of the first fundamental form of S and E are proportional. This is due to theorem 61.1. which states an allowable mapping of a portion S of a surface onto a portion S star of a surface is conformal if and only if when on S and S star the same coordinate systems have been introduced. The coefficients g sub alpha beta and g star sub alpha beta for alpha equal 1 and 2 and beta equal 1 and 2 of the first fundamental forms of S and S star respectively are proportional, namely g star sub alpha beta is equal to a function eta, say, which is positive non-zero in terms of u1 and u2 times g sub alpha beta. Hence, the images of the isotropic curves, refer back to section 63 to brush up on what isotropic curves are all about, of S are isotropic curves in the plane E. We introduce the isotropic curves on S as coordinate curves and denote by u1 and u2 the corresponding coordinates. Then, in consequence of what looks a lot like an expression which is a stereographic formula, ds squared equals a fraction of 1 over a denominator of a sub 1 squared plus a sub 2 squared. Then that fraction is times du1 tilde times du2 tilde. In consequence of this, we have that g sub 1 1 equals g sub 2 2, which equals g superscript 1 1, which equals g superscript 2 2, which equals 0. And then we have the discriminant of the first fundamental form g equal to negative of the square of g sub 1 2. Furthermore, from the definition of Christoffel symbols of the first kind and Christoffel symbols of the second kind, we have Christoffel sub 112 equals partial g sub 12 partial u1, Christoffel sub 221 equals partial g sub 12 partial u2, Christoffel sub 11 superscript 1 is equal to 1 over g sub 12 times partial g sub 12 partial u1, which equals partial with respect to u1 of the logarithm of g sub 12. And finally, we have Christoffel sub 22 superscript 2 is equal to 1 over g sub 12 times partial g sub 12 partial u2, which is equal to partial with respect to u2 of the logarithm of g sub 12, while all other Christoffel symbols are 0. Hence, the differential equation from section 50, which is from chapter 5, which is on geodesic curvature and geodesics. It's a big one, but d squared u2 du1 squared minus Christoffel sub 22 superscript 1, then times the cube of du2 du1, then minus the quantity 2 times Christoffel sub 12 superscript 1 minus Christoffel sub 22 superscript 2 closed quantity times the square of du2 du1, then plus the quantity 2 times Christoffel sub 12 superscript 2 minus Christoffel sub 11 superscript 1 closed quantity times du2 du1 plus Christoffel sub 11 superscript 2 equals 0. That differential equation of geodesics takes the form here, back in section 96, takes the form u superscript 2 double prime plus capital A times the square of u2 prime plus capital B times u2 prime equals 0, where capital A is equal to partial with respect to u2 of the logarithm of g sub 12, and capital B is equal to the negative partial derivative with respect to u1 of the logarithm of g sub 12, and prime denotes the derivative with respect to u1. And from this has to be the equation of Gauss. There's nothing else that looks like this atrocious Gaussian curvature in terms of only the first fundamental form. You know, it's like, it's a great result, don't get me wrong, because it's like once you show that you have a relation for Gaussian curvature which only depends on the first fundamental form, then you know that your quantity Gaussian curvature is essentially, it's like dependent only on intrinsic characteristics of your surface, at least when, you know, the equation of Gauss here, it's defined upon three-dimensional Euclidean real space. Okay, but from this, we're in section 96, we find our Gaussian curvature capital K is equal to 1 over g sub 12 to the fourth, and then times a discriminant 3 by 3 here, which I'm going to read entry-wise, column-wise. So we have 0, then g sub 12, then 0. Then in the second column, g sub 12, then 0, then partial g sub 12, partial u1. And then in the third column, we have partial g sub 12, partial u2, then 0, then partial square g sub 12, partial u1, partial u2. and that is the end of the discriminant. So after you expand this out, then it all resolves down to be equal to -1 over g sub 1 2 cubed, then times the quantity g sub 1 2 times partial squared g sub 1 2 partial u1 partial u2 minus partial g sub 1 2 partial u1 times partial g sub 1 2 partial u2 closed quantity. Or, in all, our Gaussian curvature capital K is equal to -1 over g sub 1 2 then times partial squared of the logarithm of g sub 1 2 partial u1 partial u2. In order to have the same coordinates on S and our plane capital E, we proceed in the plane capital E from Cartesian coordinates x1 and x2 to isotropic ones, namely u1 which is equal to x1 plus ix2 and u2 which is equal to x1 minus ix2, where I of course is the imaginary I equal to the square root of -1. Then the equation of a circle, x1 squared plus x2 squared plus a1 times x1 plus a2 times x2 plus a3 is equal to 0. This takes the form u1 times u2 plus a times u1 plus b times u2 plus d equals 0. In order to compare the earlier relation 96.1 and 96.5, which is above, we write 96.5 above in the form of a differential equation. By successive differentiation with respect to u1, we obtain u2 prime is equal to negative of a fraction with a numerator of u2 plus a and then a denominator of u1 plus b. u2 double prime is equal to 2 times a fraction of a numerator being u2 plus a and a denominator being the square of u1 plus b. And finally, we have u2 triple prime is equal to -6 times a fraction with a numerator of u2 plus a and a denominator which is the quantity u1 plus b closed quantity cubed. Hence, the circles in the plane capital E can be represented by the differential equation u2 triple prime equals 3/2 times a fraction which in the numerator is u2 double prime squared over a denominator of u2 prime. This representation does not involve the coefficients lowercase a, lowercase b, and lowercase d. And in order to compare the differential equation we just obtained and the one from the very beginning of this section, 96.1, we differentiate 96.1 with respect to u1, finding that the result of this, we have u2 triple prime plus the quantity partial capital A partial u2 then times u2 prime plus partial capital A partial u1 closed quantity then times the square of u2 prime then plus 2 times capital A times u2 prime then times u2 double prime plus the quantity partial capital B partial u2 times u2 prime plus partial capital B partial u1 closed quantity then times u2 prime plus capital B times u2 double prime equals 0. If we replace u2 double prime by means of expression 96.1, we obtain u2 triple prime plus the quantity partial capital A partial u2 minus 2 times capital A squared closed quantity times the cube of u2 prime plus quantity partial capital A partial u1 minus 3 times capital A times capital B plus partial capital B partial u2 closed quantity times the square of u2 prime plus quantity partial capital B partial u1 minus capital B squared closed quantity times u2 prime equals 0. Since we have the same coordinate systems on capital S and capital E, and since we assumed the images of the geodesics on capital S to be circles in E, the relation above 96.7 must be identically satisfied when we insert u2 triple prime according to the relation above, which is 96.8, and u2 double prime according to relation 96.1. From this we obtain conditions for capital A and capital B. We find that the quantity partial capital A partial u2 minus capital A squared over 2 closed quantity then times u2 prime cubed plus quantity partial capital A partial u1 plus partial capital B partial u2 closed quantity times u2 prime squared plus quantity partial capital B partial u1 plus capital B squared over 2 closed quantity then times u2 prime equals 0. From relation 96.2, we see that the coefficient of u2 prime squared vanishes. vanishes. The vanishing of the other two coefficients leads to the conditions where we have the partial with respect to u2 of 1 over capital A is equal to negative 1/2, and the partial with respect to u1 of 1 over capital B is equal to positive 1/2, because we may assume that capital A and capital B are non-zero. By integrating the preceding expressions, we obtain that 1 over capital A is equal to negative 1/2 times the quantity u2 plus capital C1 of u1 closed quantity, and 1 over capital B is equal to 1/2 times the quantity u1 plus capital C sub 2 in terms of u2 closed quantity. Or, in consequence of expression 96.2, partial u2 of the logarithm of g sub 1, 2 is equal to the negative fraction which has 2 in the numerator all over a denominator of u2 plus capital C sub 1 in terms of u1. We also have that partial with respect to u1 of the logarithm of g sub 1, 2 is equal to the negative fraction with 2 in the numerator and the denominator of u1 plus capital C sub 2 in terms of u2. If we integrate once more, we find that the logarithm of g sub 1, 2 is equal to negative 2 times the logarithm of the quantity u2 plus capital C sub 1 in terms of u1 closed quantities minus 2 times the logarithm of capital C sub 3 in terms of u1. This is all equal to negative 2 times the logarithm of the quantity capital C sub 3 in terms of u1, then times an inner quantity u2 plus capital C sub 1 in terms of u1 close all quantities. And the logarithm of g sub 1, 2 is equal to negative 2 times the logarithm of square bracket quantity capital C sub 4 in terms of u2, then times the quantity u1 plus capital C sub 2 in terms of u2, close it inner quantity, and close the argument on the logarithm, which is in the square brackets respectively. In order that these expressions be identical, the argument of the logarithm on the right hand side in the square brackets must be a bilinear form in u1 and u2. Namely, the log of g sub 1, 2 is equal to negative 2 times the logarithm of quantity alpha sub 1, 2 times u1 times u2 plus alpha sub 1 times u1 plus alpha sub 2 times u2 plus alpha sub 0 closed quantity. Inserting this into expression 96.3, we find that the Gaussian curvature becomes a constant, namely capital K equals 2 times the quantity alpha sub 0 times alpha sub 1, 2 minus alpha sub 1 times alpha sub 2 closed quantity. This completes the proof of theorem 96.1. We now consider the aforementioned mapping of Poincaré, which enables us to gain an intuitive understanding of the hyperbolic non-Euclidean geometry. We set in the above expression 96.10 alpha sub 1, 2 equal to 0, alpha sub 1 equal to I times lowercase c, alpha sub 2 equal to negative I times lowercase c, and alpha sub 0 equal to 0. Then by expression 96.4, the first fundamental form is given by the expression ds squared equals 2 times g sub 1, 2 times du1 du2, which equals negative of the fraction 2 in the numerator over a denominator of lowercase c squared times the quantity u1 minus u2 closed quantity squared, then times du1 du2. And this expression for the first fundamental form is ultimately equal to a fraction of a numerator being dx1 squared plus dx2 squared all over a denominator of 2 times lowercase c squared times x2 squared. And in consequence of expression 96.3, capital K is equal to negative 2 times lowercase c squared, which is negative and non-zero. The differential equation at the beginning of this section, 96.1, of the geodesics on capital S takes the form u2 double prime plus 2 over quantity u1 minus u2 closed quantity, then times a square bracket quantity, which is u2 prime squared plus u2 prime closed square bracket quantity equals 0. And if we insert into the expression that I just read the derivatives of u2 according to expression 96.6, we find that the images of the geodesics on capital S are those circles from expression 96.5 in the plane capital E for which lowercase a equals lowercase b. That is, which have the equation where u1 times u2 plus lowercase a times the quantity u1 plus u2 closed quantity plus lowercase d equals 0. Or, in terms of the coordinates x1 and x2, x1 squared plus x2 squared plus 2 times lowercase a times x1 plus lowercase d equals 0, for which refer back to expression 96.4. Hence, the center of each of these circles lies on the x1 axis. The limit cases of these circles circles, that is, the straight lines where x1 is equal to a constant, also figure among the images of the geodesics of capital S star. We restrict the mapping of Poincaré to the upper half plane, namely where x2 is greater than or equal to 0. In this manner, we obtain the desired intuition of the hyperbolic non-Euclidean geometry. Uh-oh, we can't have intuition in math. Don't tell anyone. The half plane where x2 is non-zero when the metric defined by the expression above 96.12 has been introduced is called the half plane of Poincaré, for which we can refer to the reference Théorie de Curvature by Monsieur Poincaré. The image of a geodesic on S passing through 2 points, capital P tilde and capital Q tilde, is a semicircle, capital H in terms of capital P and capital Q, with center on the x1 axis and passing through the image points P and Q of P tilde and Q tilde, respectively. In analogy with the displacements in the Euclidean plane, which were brought up in section 3, there are transformations under which the first fundamental form, given in expression 96.12, is invariant. These are the so-called, quote, linear transformations, unquote, namely u superscript mu star is equal to a fraction with the numerator alpha times u superscript mu plus beta all over a denominator of gamma times u superscript mu plus delta, where the discriminant column-wise alpha and then gamma, and then in the next column beta and then delta, this discriminant is greater than 0, where mu is equal to 1 or 2, and this is not Einstein's summation notation, so do not sum. And these linear transformations are such that the coefficients alpha, beta, gamma, and delta are real. This transformation group is considered in function theory. The transformations are conformal, namely angles are preserved, and transform circles into circles. We can refer back to sections 61 and 65. 61, of course, on conformal mapping, and 65 being on conformal mapping of a sphere into a plane. Also touched on stereographic and Mercator projection. Pretty good sections, actually. In order to determine the non-Euclidean distance between two arbitrary points P and Q in the image plane capital E, we first impose on the image plane capital E a non-Euclidean motion under which the semicircle given by capital H in terms of P and Q is transformed into the positive ray of the x2 axis. We denote by u sub a superscript 1 and u sub b superscript 1, which u sub b superscript 1 is greater than u sub a superscript 1, the points of intersection of function capital H for our semicircle in terms of P and Q and the x1 axis, for which refer to figure 99 on the next page. I'll just superimpose that here. Then this transformation is of the form u1 star equals a fraction with a numerator of u subscript a superscript 1 minus u1 all over a denominator of u1 minus u subscript b superscript 1. The non-Euclidean distance between P and Q is preserved under this transformation and is afterwards given by the expression s equals 1 over lowercase c times the square root of 2 then times the magnitude of the integral from x sub 2 star evaluated at the point capital P to x sub 2 star evaluated at the point capital Q, integral of dx2 over x2. In other words, the integral is 1 over x2 dx2. And then take the magnitude of evaluating that integral from x2 star evaluated at P to x2 star evaluated at Q. This non-Euclidean distance lowercase s then resolves out to be, because it's just, integral of 1 over, it's just, integral of 1 over x. So it evaluates out to be being also a definite integral. 1 over lowercase c times the square root of 2 times the magnitude of the logarithm of a fraction with the numerator of x sub 2 superscript star evaluated at capital Q over a denominator of x sub 2 superscript star evaluated at capital P. Apart from the factor 1 over a denominator of lowercase c times the square root of 2, this is nothing but the cross ratio of the points P and Q and the 2 points of intersection of H in terms of P and Q and the x1 axis. Indeed, the cross ratio of 4 points on a circle is invariant under the above linear transformations, as can be shown. If P or Q tends to one of the aforementioned points of intersection, lowercase s tends to infinity. Consequently, the x1 axis represents the improper line with respect to the metric defined by the above relation 96.12. This fact can also immediately be seen from 96.12. Through every point capital P star of the plane capital E, there passes a bundle, capital B, of semicircles with centers on the x1 axis. Okay, we're just going to forgive Erwin Kreisig that this is the last page of the book, that he didn't formally define bundle, but fiber bundle, it should kind of be ringing bells. It's sort of like if you have a hairbrush and there's all the little fibers, you could get a bundle of those. It's kind of like your bundle of tangent vectors that you're thinking of here. Also could be referred to as maybe like a pencil. Anyways, there passes a bundle, capital B, of semicircles with centers on the x1 axis. Let capital H star be a circle with center on the x1 axis and which does not pass through capital P star. Obviously, the bundle B contains infinitely many semicircles which intersect H star at proper points. Exactly two semicircles, quote, parallel, unquote, to H star, each of which has an improper point in common with H star, and infinitely many, quote, hyperparallel, unquote, semicircles which do not intersect H star at all. The analogous property therefore also holds for the geodesics of the pseudospherical surface which has been mapped onto the half plane of Poincaré under consideration. Eugenio Beltrami's geodesic mapping of pseudospherical surfaces in a plane can be obtained from Poincaré's mapping. We choose a sphere, capital K star, with center capital M at an arbitrary point of the improper line capital G, where x2 is equal to 0, of the Poincaré half plane capital E, and project half plane capital E stereographically into the sphere capital K star. Refer back to section 65 on those kinds of conformal mappings into a sphere, choosing as the center of this projection one of the 2 points of intersection of capital K and the normal to capital E passing through the center capital M. The image of capital G is a great circle capital G star of capital K star. The image lowercase k star of any semicircle lowercase k with center on capital G is again a semicircle, refer again back to section 65, whose plane is orthogonal to the plane of capital G star. The original pseudospherical surface capital S, which has been mapped onto capital E, is now mapped conformally into capital K star, and the image of any geodesic on capital S is a semicircle lowercase k star. We now project the image of capital S on capital K star orthogonally into the plane of capital G star. Under this projection, the image of any semicircle lowercase k star is a segment of a straight line. This is the desired geodesic mapping of capital S into the plane, and the image of capital S is the circular disk with boundary capital G star. Spherical surfaces can also be mapped geodesically into the plane. Since all these surfaces corresponding to a certain value of capital K are isometric, for which refer back to theorems 91.1 and 94.2, it suffices to construct a geodesic mapping of a sphere capital K into a plane. Such a mapping can be obtained by a central projection of capital K onto a tangent plane capital E of capital K, where the center capital M of capital K is the center of projection. In this manner, a hemisphere of capital K is mapped onto capital E. This mapping is geodesic because every plane passing through capital M intersects capital K along a great circle and capital E along a straight line. In consequence of theorem 95.1, we therefore have the following result, which is the last formal theorem in differential geometry by Erwin Kreisig. Theorem 96.2 by Eugenio Beltrami. The portions of surfaces of constant Gaussian curvature are the only ones which can be mapped geodesically into the plane. And these are the last problems of the book. Problem 96.1. Prove that the metric defined by expression 96.12 is invariant with respect to the linear mappings of expression 96.14. The solution is as follows. We will prove that if we apply expression 96.14 to expression 96.12, we obtain negative of the fraction with a numerator of 2 times du1 du2 over a denominator of lowercase c squared times the quantity u1 minus u2 closed quantity squared, which equals another fraction, which is a numerator negative 2 times du1 star times du2 star all over a denominator of lowercase c squared times the quantity u1 star minus u2 star closed quantity squared. From expression 96.14, it follows that du superscript mu star equals a fraction with a numerator of capital D times du mu over a denominator of quantity gamma times u mu plus delta closed quantity squared, where mu is equal to 1 or 2, and u1 star minus u2 star is equal to a fraction with a numerator of capital D times quantity u1 minus u2 closed quantity over a denominator of quantity gamma times u1 u1 plus delta closed quantity times another quantity, gamma times u2 plus delta closed quantity. And in all of this, capital D is equivalent to alpha times delta minus beta times gamma. And by just following through with the computations, then we see that what we sought to prove holds. Prove that a function u2 in terms of u1 is a rational function whose numerator and denominator are linear functions if and only if the function u2 in terms of u1 satisfies a differential equation of the form given by expression 96.7. The solution is as follows. According to expression 96.5, u2 is a function of the type indicated in the enunciation of the problem and satisfies expression 96.7, or the conditions in 96.7 rather. In order to prove the converse, we have to solve 96.7, which is equivalent to 3 times u2 double prime over u2 prime minus 2 times u2 triple prime over u2 double prime equals 0. So this is very straightforward. By integration, we find that 3 times the logarithm of u2 prime minus 2 times the logarithm of u2 double prime equals c star, or u2 double prime over u2 prime to the power of 3 halves is equal to lowercase c. We integrate once more and find that negative 2 times u2 prime to the power of negative 1 half is equal to lowercase c times u1 plus d, or u2 prime is equal to a fraction with a numerator of 4 over a denominator of the quantity lowercase c times u1 plus d closed quantity squared. We integrate once more and have that u2 is equal to negative 4 over the denominator of c times the quantity c times u1 plus d closed quantity, then plus a, and this completes the proof. The last problem of differential geometry by Erwin Kreisig, problem 96.3. Prove that on a surface of constant Gaussian curvature, the geodesic circles, for which refer back to section 53, are curves of constant geodesic curvature. The solution is as follows. We consider a surface capital S of constant Gaussian curvature and introduce on capital S geodesic polar coordinates u1 and u2. Again, refer back to section 53, which in the midst of chapter 5 on geodesics, section 53 was on geodesic polar coordinates. Surprise. Then the curves where u1 are equal to a constant are geodesic circles. Since g sub 1 is equal to 1, these curves have the geodesic curvature quantity kappa sub g closed quantity subscript u1 equal to a constant equals partial u1 of the logarithm of the square root of g sub 2, for which refer to, again, expression 49.9a, which I read at the beginning of this episode. In order that the geodesic curvature of any of these curves be a constant, that is, be independent of u2, we must have that the second derivative, once with respect to u1, once with respect to u2, of the logarithm of the square root of g sub 2 is equal to 0. That is, the logarithm of the square root of g sub 2 must be a sum of two functions, each of which depends on one of the two variables u1 or u2 only. That is, the square root of g sub 2 must be a product of two such functions. And as can be seen from the relations 90.3, 90.4, 90.5, this holds in the case of surfaces of constant Gaussian curvature, namely g sub 2 even depends on u1 only. And I'll give it one of these. And that has been reading Differential Geometry by Erwin Kreisig with me, Anthony. I hope you've enjoyed watching, listening, learning along, or I hope this has helped you fall asleep. I guess this is it. See you later. Bye.